In the mountains of northern Italy, engineers implemented what they believed to be an advanced solution to alpine hydroelectric development. The Gleno Dam represented a hybrid approach, a traditional stone masonry base supporting an innovative multiple-arch concrete superstructure. The design philosophy assumed that visual monitoring and basic measurement techniques would provide adequate warning of any structural distress. Construction proceeded according to accepted practices of the era. Materials were sourced locally, workers followed established procedures, inspections occurred at regular intervals, the completed structure appeared sound and functioned as intended for its brief operational life. Water levels rose and stabilized. Power generation commenced. No obvious defects were apparent. Yet the design contained a fundamental vulnerability that monitoring systems could not detect. The junction between the masonry foundation and the concrete arches created conditions that existing instrumentation could not adequately assess. When water began to migrate through this interface, the process remained invisible to operators until structural compromise had progressed beyond recovery. The failure sequence unfolded exactly as the materials and construction methods determined it would. Operators responded to the information available to them, which indicated normal conditions even as the foundation was progressively losing integrity. The disaster resulted not from negligence or incompetence, but from a monitoring philosophy that could not reveal the actual state of a complex structural system. How can engineering surveillance systems function correctly while remaining blind to the mechanisms that ensure structural failure? The Gleno Dam represented the convergence of engineering ambition and industrial necessity in the early decades of the 20th century. Located in the Valle di Scalve in the Italian Alps, the structure was conceived as part of the broader electrification campaign that swept through mountainous regions of Europe following the First World War. The facility was designed to harness the seasonal water flows of the Po River, transforming kinetic energy into electrical power for the expanding industrial centers of northern Italy. The original design, submitted in 1913, called for a conventional masonry gravity dam with a curvilinear planimetric layout. This approach reflected established engineering practice, relying on massive stone construction to resist the hydrostatic forces exerted by the retained water. The design philosophy was straightforward. The weight and geometric configuration of the structure would provide adequate safety margins against both sliding and overturning failure modes. Construction began in 1917, proceeding with the excavation and placement of the stone masonry foundation intended to anchor the structure to the valley floor. However, the project underwent a fundamental transformation during the construction phase. The original gravity design was abandoned in favor of a hybrid configuration that combined the partially completed masonry base with a reinforced concrete, multiple-arch superstructure. This decision represented a significant departure from the conservative engineering approach embodied in the initial design. The new configuration featured 25 individual arches spanning between concrete buttresses, creating an S-shaped planimetry approximately 220 meters in total length and reaching a maximum height of 46 meters above the foundation level. The technical rationale for this design modification centered on material efficiency and construction economy. The multiple-arch configuration promised to achieve the required structural strength while utilizing significantly less concrete than would be required for a conventional gravity dam of equivalent height. The arches would transfer hydrostatic loads to discrete buttress points, which in turn would distribute these forces through the masonry foundation to the underlying rock formation. This load path assumed that the interface between the concrete superstructure and the masonry base would function as a monolithic unit, with no significant differential settlement or loss of contact between the dissimilar materials. The design assumptions embedded within this hybrid approach reflected the state of understanding regarding reinforced concrete behavior in the early 1920s. Engineers possessed extensive experience with masonry construction techniques, having developed sophisticated approaches to stone cutting, placement, and mortar formulation over centuries of practice. However, the application of reinforced concrete to major hydraulic structures remained relatively experimental, with limited long-term performance data available to inform design decisions. The multiple-arch configuration introduced several critical dependencies that distinguished it from conventional gravity dam designs. The structural integrity of the system relied on the coordinated performance of multiple discrete elements rather than the monolithic behavior of a single massive structure. Each arch element was designed to span between buttress supports, creating a series of individual load-bearing units that collectively contained the reservoir pressure. This approach required precise construction tolerances to ensure uniform load distribution and prevent stress concentrations that could initiate progressive failure modes. The instrumentation philosophy adopted for the Gleno Dam reflected the limited monitoring capabilities available during this period. Visual inspection constituted the primary means of structural assessment, supplemented by basic measurement techniques for monitoring water levels and flow rates. The design assumed that any significant structural distress would manifest through observable surface indications such as cracking, displacement, or unusual seepage patterns. This monitoring approach had proven adequate for masonry gravity structures, where failure modes typically developed gradually and provided clear visual warning signs. The foundation design incorporated several assumptions regarding the behavior of the masonry-concrete interface. Engineers anticipated that the weight of the concrete superstructure would create sufficient compression to ensure intimate contact between the two materials, preventing the development of separation or sliding planes. The masonry base was designed to provide a stable bearing surface, distributing the concentrated loads from the concrete buttresses across a broader area of the valley floor. This load distribution mechanism assumed that the masonry would behave as a competent structural material, capable of transmitting forces without significant deformation or deterioration. The construction sequence adopted for the hybrid design created temporary conditions that differed significantly from the final operational configuration. The masonry foundation was completed first, followed by the placement of concrete for the buttresses and arch elements. During this construction phase, the partially completed structure experienced loading conditions that would not occur during normal operation. The temporary nature of these conditions was considered acceptable, as the design focused primarily on the performance requirements of the completed facility rather than intermediate construction stages. The quality control procedures implemented during construction reflected standard practice for the period, emphasizing dimensional accuracy and material specifications rather than integrated system performance. Stone selection and placement followed established masonry techniques, with mortar joint width and composition controlled according to traditional specifications. Concrete placement procedures focused on achieving specified strength and durability characteristics, with limited attention to the long-term behavior of the masonry-concrete interface. The design philosophy assumed that the operational environment would remain within the parameters established during the design phase. Water levels were expected to fluctuate within predictable seasonal patterns, with reservoir filling and drawdown cycles following established hydrological data. The thermal environment was considered relatively benign, with seasonal temperature variations falling within the expected range for alpine conditions. Chemical attack from dissolved minerals in the water was not considered a significant threat to structural integrity, based on the water quality characteristics observed in similar regional facilities. The safety margin calculations incorporated standard load factors and material property assumptions current at the time of design. The hydrostatic pressure distribution was calculated using established principles of fluid statics, with appropriate factors applied to account for dynamic effects during reservoir filling operations. The structural analysis assumed linear elastic behavior for both the masonry and concrete materials, with failure criteria based on allowable stress limitations rather than ultimate strength considerations. However, the design contained several implicit assumptions that would prove critical to the subsequent failure sequence. The hybrid configuration assumed that differential thermal expansion between the masonry base and concrete superstructure would remain within tolerable limits. The analysis did not fully account for the potential development of preferential seepage paths along the material interface, nor did it consider the progressive deterioration of bond strength that could occur under cyclic loading conditions. The operational procedures developed for the facility reflected the monitoring limitations inherent in the design philosophy. Operators were trained to observe surface conditions and monitor basic operational parameters, but they lacked instrumentation capable of detecting subsurface deterioration or progressive bond failure. The procedures assumed that any condition requiring immediate attention would manifest through readily observable symptoms, providing adequate warning time for corrective action. The regulatory environment within which the Gleno Dam was designed and constructed provided limited oversight of innovative design approaches. The approval process focused primarily on static analysis calculations and basic safety factors, without requiring comprehensive evaluation of failure modes specific to hybrid structural configurations. This regulatory framework had proven adequate for conventional dam designs, but it did not address the unique vulnerabilities introduced by the multiple arch configuration and masonry concrete interface. These design assumptions, considered reasonable and conservative by the engineering standards of the early 1920s, established the conditions that would determine the facility's operational characteristics and ultimate failure mode. The combination of innovative structural configuration, limited monitoring capability, and conventional regulatory oversight created a system where progressive deterioration could advance beyond the detection threshold before manifesting through observable symptoms. The stage was set for a failure sequence that would unfold according to the physical laws governing material behavior and interface mechanics, rather than the operational procedures and monitoring protocols intended to ensure structural integrity. The Gleno Dam represented the convergence of engineering ambition and industrial necessity in the early decades of the 20th century. Located in the Valle di Scalve in the Italian Alps, the structure was conceived as part of the broader electrification campaign that swept through mountainous regions of Europe following the First World War. The facility was designed to harness the seasonal water flows of the Po River, transforming kinetic energy into electrical power for the expanding industrial centers of northern Italy. The original design, submitted in 1913, called for a conventional masonry gravity dam with a curvilinear planimetric layout. This approach reflected established engineering practice, relying on massive stone construction to resist the hydrostatic forces exerted by the retained water. The design philosophy was straightforward. The weight and geometric configuration of the structure would provide adequate safety margins against both sliding and overturning failure modes. Construction began in 1917, proceeding with the excavation and placement of the stone masonry foundation, intended to anchor the structure to the valley floor. However, the project underwent a fundamental transformation during the construction phase. The original gravity design was abandoned in favor of a hybrid configuration that combined the partially completed masonry base with a reinforced concrete multiple arch superstructure. This decision represented a significant departure from the conservative engineering approach embodied in the initial design. The new configuration featured 25 individual arches spanning between concrete buttresses, creating an S-shaped planimetry approximately 220 meters in total length, and reaching a maximum height of 46 meters above the foundation level. The technical rationale for this design modification centered on material efficiency and construction economy. The multiple arch configuration promised to achieve the required structural strength while utilizing significantly less concrete than would be required for a conventional gravity dam of equivalent height. The arches would transfer hydrostatic loads to discrete buttress points, which in turn would distribute these forces through the masonry foundation to the underlying rock formation. This load path assumed that the interface between the concrete superstructure and the masonry base would function as a monolithic unit, with no significant differential settlement or loss of contact between the dissimilar materials. The design assumptions embedded within this hybrid approach reflected the state of understanding regarding reinforced concrete behavior in the early 1920s. Engineers possessed extensive experience with masonry construction techniques, having developed sophisticated approaches to stone cutting, placement, and mortar formulation over centuries of practice. However, the application of reinforced concrete to major hydraulic structures remained relatively experimental, with limited long-term performance data available to inform design decisions. The multiple arch configuration introduced several critical dependencies that distinguished it from conventional gravity dam designs. The structural integrity of the system relied on the coordinated performance of multiple discrete elements rather than the monolithic behavior of a single massive structure. Each arch element was designed to span between buttress supports, creating a series of individual load-bearing units that collectively contained the reservoir pressure. This approach required precise construction tolerances to ensure uniform load distribution and prevent stress concentrations that could initiate progressive failure modes. The instrumentation philosophy adopted for the Gleno Dam reflected the limited monitoring capabilities available during this period. Visual inspection constituted the primary means of structural assessment, supplemented by basic measurement techniques for monitoring water levels and flow rates. The design assumed that any significant structural distress would manifest through observable surface indications such as cracking, displacement, or unusual seepage patterns. This monitoring approach had proven adequate for masonry gravity structures, where failure modes typically developed gradually and provided clear visual warning signs. The foundation design incorporated several assumptions regarding the behavior of the masonry-concrete interface. Engineers anticipated that the weight of the concrete superstructure would create sufficient compression to ensure intimate contact between the two materials, preventing the development of separation or sliding planes. The masonry base was designed to provide a stable bearing surface, distributing the concentrated loads from the concrete buttresses across a broader area of the valley floor. This load distribution mechanism assumed that the masonry would behave as a competent structural material, capable of transmitting forces without significant deformation or deterioration. The construction sequence adopted for the hybrid design created temporary conditions that differed significantly from the final operational configuration. The masonry foundation was completed first, followed by the placement of concrete for the buttresses and arch elements. During this construction phase, the partially completed structure experienced loading conditions that would not occur during normal operation. The temporary nature of these conditions was considered acceptable, as the design focused primarily on the performance requirements of the completed facility rather than intermediate construction stages. The quality control procedures implemented during construction reflected standard practice for the period, emphasizing dimensional accuracy and material specifications rather than integrated system performance. Stone selection and placement followed established masonry techniques, with mortar joint width and composition controlled according to traditional specifications. Concrete placement procedures focused on achieving specified strength and durability characteristics, with limited attention to the long-term behavior of the masonry-concrete interface. The design philosophy assumed that the operational environment would remain within the parameters established during the design phase. Water levels were expected to fluctuate within predictable seasonal patterns, with reservoir filling and drawdown cycles following established hydrological data. The thermal environment was considered relatively benign, with seasonal temperature variations falling within the expected range for alpine conditions. Chemical attack from dissolved minerals in the water was not considered a significant threat to structural integrity, based on the water quality characteristics observed in similar regional facilities. The safety margin calculations incorporated standard load factors and material property assumptions current at the time of design. The hydrostatic pressure distribution was calculated using established principles of fluid statics, with appropriate factors applied to account for dynamic effects during reservoir filling operations. The structural analysis assumed linear elastic behavior for both the masonry and concrete materials, with failure criteria based on allowable stress limitations rather than ultimate strength considerations. However, the design contained several implicit assumptions that would prove critical to the subsequent failure sequence. The hybrid configuration assumed that differential thermal expansion between the masonry base and concrete superstructure would remain within tolerable limits. The analysis did not fully account for the potential development of preferential seepage paths along the material interface, nor did it consider the progressive deterioration of bond strength that could occur under cyclic loading conditions. The operational procedures developed for the facility reflected the monitoring limitations inherent in the design philosophy. Operators were trained to observe surface conditions and monitor basic operational parameters, but they lacked instrumentation capable of detecting subsurface deterioration or progressive bond failure. The procedures assumed that any condition requiring immediate attention would manifest through readily observable symptoms, providing adequate warning time for corrective action. The regulatory environment within which the Gleno Dam was designed and constructed provided limited oversight of innovative design approaches. The approval process focused primarily on static analysis calculations and basic safety factors, without requiring comprehensive evaluation of failure modes specific to hybrid structural configurations. This regulatory framework had proven adequate for conventional dam designs, but it did not address the unique vulnerabilities introduced by the multiple arch configuration and masonry concrete interface. These design assumptions, considered reasonable and conservative by the engineering standards of the early 1920s, established the conditions that would determine the facility's operational characteristics and ultimate failure mode. The combination of innovative structural configuration, limited monitoring capability, and conventional regulatory oversight created a system where progressive deterioration could advance beyond the detection threshold before manifesting through observable symptoms. The stage was set for a failure sequence that would unfold according to the physical laws governing material behavior and interface mechanics, rather than the operational procedures and monitoring protocols intended to ensure structural integrity. The Gleno Dam's operational phase began with a series of seemingly minor conditions that, while individually acceptable within contemporary engineering standards, collectively established the preconditions for catastrophic failure. These latent conditions existed within the organizational, technical, and procedural frameworks that governed the facility's construction and early operation, creating vulnerabilities that remained invisible until the final failure sequence activated them. The construction quality control procedures, while following established practices of the era, contained several systematic weaknesses that would prove critical. The masonry foundation work proceeded according to traditional stone construction techniques, with individual blocks selected and placed based on visual assessment of fit and structural adequacy. However, the interface preparation between the masonry base and the concrete superstructure received limited attention beyond standard surface cleaning procedures. The assumption that adequate bond strength would develop naturally between the two materials led to minimal specification of interface treatment methods or quality verification procedures. Documentation from the construction period indicates that the concrete placement for the multiple arch structure occurred during variable weather conditions, with some portions of the work completed during periods of reduced temperature that could affect concrete curing characteristics. The construction schedule, compressed by post-war reconstruction pressures, prioritized completion speed over extended curing periods that might have enhanced long-term bond development at the critical material interface. These schedule pressures were considered normal for the period and did not trigger any modification of standard construction procedures. The workforce employed during construction represented a mixture of experienced stonemasons and concrete workers relatively new to reinforced concrete techniques. The masonry crews possessed extensive traditional skills, but the concrete placement crews had limited experience with the specific requirements of hydraulic structures. This skill distribution created potential inconsistencies in construction quality, particularly at the interface zone where traditional masonry techniques intersected with emerging concrete technology. The supervision structure assumed that standard trade practices would ensure adequate quality without requiring specialized interface construction procedures. The material supply chain reflected the post-war industrial conditions of northern Italy, with cement sourced from regional producers and aggregates obtained from local quarry operations. Quality control testing of these materials focused on basic strength characteristics rather than long-term durability parameters or compatibility with the masonry mortars used in the foundation construction. The assumption that materials meeting individual specifications would perform adequately in combination led to minimal testing of the integrated material system that would govern interface behavior. The inspection and approval procedures implemented during construction emphasized dimensional compliance and visual assessment of surface conditions. Inspectors examined the completed masonry work for proper stone placement and mortar joint consistency, and they evaluated the concrete placement for surface finish and dimensional accuracy. However, the inspection protocol contained no specific provisions for evaluating the quality of the masonry concrete interface or for detecting incipient separation that might develop as the concrete cured and developed its final strength characteristics. The facility's alarm and monitoring systems reflected the state of instrumentation technology available in the early 1920s. Water level measurement relied on simple staff gauges and mechanical float systems that provided basic operational information but offered no capability for detecting subtle changes that might indicate developing structural problems. Flow measurement systems consisted of basic mechanical devices adequate for operational control, but lacking the sensitivity required to detect unusual seepage patterns that could signal progressive deterioration. The operator training program focused primarily on normal operational procedures, including reservoir filling schedules, power generation protocols, and routine maintenance activities. The training curriculum contained limited material addressing abnormal conditions or emergency procedures, reflecting the prevailing assumption that structural failures would develop gradually and provide clear warning signs. Operators received minimal instruction regarding the specific vulnerabilities associated with the hybrid structural configuration, or the potential failure modes that might affect multiple arch designs. The organizational structure governing facility operations separated routine operational responsibilities from structural engineering oversight. Day-to-day operations were managed by personnel with primary expertise in mechanical and electrical systems, while structural concerns remained the province of design engineers who were not continuously present at the facility. This division of responsibility assumed that structural issues would be readily apparent to operational personnel and could be addressed through standard engineering consultation procedures when necessary. The maintenance procedures developed for the facility emphasized mechanical components such as valves, generators, and control systems rather than structural elements. Structural maintenance consisted primarily of visual inspection for obvious signs of distress, such as surface cracking or unusual movement. The inspection intervals were based on conventional practice for masonry structures, which typically exhibit gradual deterioration patterns that provide extended warning periods before reaching critical conditions. The communication protocols established for reporting structural concerns required operational personnel to identify and document obvious problems before initiating engineering consultation. This procedure assumed that structural distress would manifest through readily observable symptoms and that operational staff possessed sufficient expertise to distinguish between normal operational variations and conditions requiring immediate engineering attention. The threshold for triggering engineering involvement was set relatively high, reflecting the assumption that most operational variations fell within normal parameters. The regulatory oversight framework applicable to the Gleno Dam provided minimal continuing surveillance following initial construction approval. Post-construction inspection requirements were limited in scope and frequency, focusing primarily on operational compliance rather than ongoing structural assessment. The regulatory assumption was that properly designed and constructed facilities would operate safely within their design parameters without requiring intensive ongoing oversight. This framework had proven adequate for conventional structures, but did not account for the unique monitoring requirements associated with experimental design configurations. The record-keeping systems implemented at the facility captured basic operational data, such as water levels, power generation output, and routine maintenance activities. However, the documentation system contained no provisions for systematically recording observations that might indicate gradual structural changes or for maintaining historical records that could reveal long-term trends in facility behavior. This limitation reflected the prevailing view that structural performance was either adequate or obviously deficient, with little recognition of the importance of monitoring gradual deterioration processes. The emergency response procedures developed for the facility addressed scenarios such as equipment failures, power outages, and flooding events, but they contained minimal provisions for responding to structural emergencies. The emergency planning process assumed that structural problems would develop gradually enough to permit orderly response measures and that advance warning would be available through routine monitoring activities. The procedures did not address scenarios where structural integrity might deteriorate rapidly without clear advance indications. The interface design between the masonry foundation and concrete superstructure incorporated no specific provisions for accommodating differential movement or for maintaining structural continuity under varying thermal and hydraulic conditions. The design assumed that the two materials would behave as a monolithic unit throughout all anticipated loading conditions. This assumption failed to account for the different thermal expansion characteristics of stone masonry and reinforced concrete, or for the potential effects of water infiltration on bond strength at the material interface. The water management procedures for the facility prioritized operational efficiency and power generation capacity over structural considerations. Reservoir filling schedules were based on hydrological data and power demand patterns, rather than structural loading limitations or the potential effects of rapid water level changes on the foundation superstructure interface. The operational assumption was that the structure could accommodate any filling rate within its design capacity without requiring special consideration of loading sequence or rate effects. The quality assurance procedures implemented during construction focused on individual components rather than integrated system performance. Stone masonry work was evaluated according to traditional masonry standards, while concrete placement was assessed according to emerging reinforced concrete criteria. However, no specific procedures existed for evaluating the performance of the integrated system or for detecting potential incompatibilities between the different construction materials and techniques. These latent conditions, individually within acceptable parameters for the time period, combined to create a facility where progressive deterioration could advance beyond the detection capability of existing monitoring systems. The separation of operational and structural responsibilities, combined with limited instrumentation capability and conventional maintenance procedures, established conditions where critical structural changes could occur without triggering immediate recognition or response. The organizational and technical frameworks that had proven adequate for conventional structures were poorly suited to the unique monitoring and maintenance requirements of the experimental hybrid design configuration implemented at Gleno. The morning of December 1, 1923, began with conditions that appeared entirely normal to the operational staff at the Gleno Dam. The reservoir had reached its design capacity approximately 40 days earlier, following the first complete filling cycle since construction completion. Water levels had stabilized at the intended operational elevation, with no unusual fluctuations or operational anomalies reported during the preceding weeks. The facility had been generating electrical power according to design specifications, with mechanical systems operating within expected parameters. At approximately 7:05 a.m. local time, according to the testimony of Giuseppe Olmo, the facility watchman who was present at the dam site, the first visible indication of structural distress appeared in the central portion of the multiple arch structure. Olmo's account, recorded during subsequent legal proceedings, described the collapse as occurring in 3 distinct phases, each involving the progressive failure of multiple structural elements, rather than a single catastrophic event. The initial phase involved the failure of the 11th concrete buttress, located approximately at the center of the dam's S-shaped configuration. This buttress supported 2 adjacent arch spans, and its collapse created an initial breach estimated at approximately 14 meters in width. The failure of this single buttress immediately transferred additional loading to the adjacent structural elements, creating stress concentrations that exceeded the design capacity of the surrounding components. The physical evidence suggests that the initial buttress failure resulted from progressive undermining of its foundation support rather than material failure of the concrete structure itself. Post-event examination of the failure zone revealed that water had infiltrated the interface between the masonry foundation and the concrete buttress, creating conditions that compromised the load transfer mechanism between these dissimilar materials. This infiltration pattern indicated that seepage had been occurring for an extended period prior to the visible structural collapse. The failure mechanism appears to have initiated through the development of preferential seepage paths along the masonry-concrete interface. These seepage paths would have been invisible to surface observation and undetectable using the monitoring instrumentation available at the facility. As water penetrated this interface, it gradually reduced the effective contact area between the concrete buttress and its masonry foundation, concentrating the structural loads on progressively smaller bearing surfaces. The second phase of the collapse, following within minutes of the initial buttress failure, involved the progressive collapse of buttresses 8 through 12. This sequence suggests that the failure propagated through load redistribution effects, rather than through direct hydraulic undermining of each individual foundation. As each buttress failed, the loads it had been carrying were transferred to adjacent elements, creating a cascade effect that overwhelmed the remaining structural capacity. The rapidity of this second phase indicates that several of the buttresses involved were already operating near their effective load capacity due to foundation degradation that had occurred prior to the visible collapse. The failure sequence suggests that the foundation undermining process had affected multiple buttress locations simultaneously, reducing the overall structural redundancy of the system to the point where the loss of any single element would trigger progressive collapse of the entire central section. The final phase involved the collapse of buttresses 4 through 7, completing the destruction of the central 80-meter section of the dam structure. This phase occurred within approximately 30 seconds of the initial failure, according to witness accounts, indicating that the remaining structure lacked sufficient capacity to redistribute the loads from the previously failed elements. The speed of this final collapse phase suggests that these buttresses had also experienced significant foundation degradation prior to the visible failure sequence. The hydraulic conditions present at the time of failure contributed to both the initiation and propagation of the collapse sequence. The reservoir was at its maximum design level, creating maximum hydrostatic pressure on the structure and maximum hydraulic gradient across the foundation interface. These conditions would have accelerated any existing seepage processes and maximized the rate of foundation undermining once the initial failure occurred. The physical evidence recovered from the failure site indicates that the concrete elements themselves remained largely intact during the collapse, with failure occurring primarily through loss of foundation support rather than through material overstress of the concrete structure. This failure pattern confirms that the multiple arch design itself was structurally adequate for the applied loads, but that the foundation interface proved incapable of providing the assumed level of support. The seepage pattern observed at the failure interface suggests that water infiltration had been occurring for an extended period prior to the visible collapse. The development of these seepage paths would have been gradual, beginning with minor infiltration at points of imperfect contact between the masonry and concrete surfaces. Over time, the seepage would have progressively enlarged these contact defects, reducing the effective bearing area and concentrating loads on smaller foundation zones. The environmental conditions present during the weeks preceding the failure may have contributed to accelerating the foundation degradation process. The autumn period prior to December 1923 experienced normal seasonal temperature variations that would have caused differential thermal expansion between the masonry foundation and concrete superstructure. These thermal cycles could have gradually opened microgaps at the material interface, providing additional pathways for water infiltration. The operational procedures in effect at the time of failure contained no provisions for detecting the type of progressive foundation degradation that ultimately caused the collapse. Visual inspection protocols focused on surface conditions that would be readily apparent to operational personnel, while the critical deterioration was occurring beneath the concrete buttresses where it remained invisible until structural failure occurred. The reservoir management procedures implemented during the weeks preceding the failure prioritized operational efficiency over structural considerations. Water levels were maintained at maximum capacity to optimize power generation, creating sustained maximum loading on the foundation interface. Alternative operating procedures that might have reduced hydraulic pressures during periods of suspected seepage were not considered, as no indication of developing problems had been detected through routine monitoring activities. The failure sequence unfolded according to the physical laws governing foundation bearing capacity and load redistribution in statically indeterminate structures. Once the seepage-induced foundation degradation reached a critical threshold, the collapse became inevitable, regardless of operational procedures or emergency response measures. The failure mechanism was fundamentally controlled by the progressive loss of contact between the concrete buttresses and their masonry foundations. The information available to operational personnel at the time of the initial failure provided no indication of the actual structural condition or of the imminent complete collapse of the central dam section. Surface observations during the days and weeks preceding December 1st had revealed no obvious signs of distress, and operational parameters remained within normal ranges. The facility appeared to be performing according to design specifications up to the moment of initial structural failure. The cascade failure mechanism that developed following the initial buttress collapse occurred too rapidly to permit any meaningful intervention or damage limitation measures. The time interval between initial failure and complete collapse of the central section was insufficient for operators to assess the situation or implement emergency procedures that might have reduced the magnitude of the resulting flood wave. The physical evidence indicates that the failure process had advanced beyond any possible recovery point well before the first visible signs of structural distress appeared. The foundation undermining process had progressed to the point where multiple buttresses were operating with severely compromised support conditions, making the collapse of the entire central section inevitable once any single element failed. This divergence between apparent structural adequacy and actual structural condition represents the fundamental characteristic that distinguished the Gleno failure from conventional structural failures that provide clear advance warning through observable distress symptoms. The facility continued to appear structurally sound and operationally normal even as the critical foundation interface deteriorated beyond the point of recovery. The catastrophic release of approximately 4.5 million cubic meters of water from the Gleno reservoir initiated a complex sequence of physical processes that transformed potential energy into devastating kinetic force. The failure mechanism that destroyed the dam's central section created a breach opening of sufficient size to permit essentially uncontrolled reservoir discharge, converting the retained water mass into a flood wave that would propagate through the downstream valley system according to fundamental principles of fluid mechanics and momentum conservation. The initial breach formation resulted from the progressive collapse of the central buttresses, creating an irregular opening approximately 80 meters wide at its maximum extent. The geometry of this breach, determined by the structural failure pattern rather than hydraulic optimization, created flow conditions that differed significantly from controlled spillway discharge scenarios. The absence of flow guidance structures or energy dissipation features meant that the entire hydraulic head of the reservoir would be converted directly into kinetic energy as water accelerated through the breach opening. The hydraulic analysis of the breach discharge process reveals flow rates that peaked at approximately 21,000 cubic meters per second during the initial phases of reservoir emptying. This discharge magnitude exceeded the natural channel capacity by more than 2 orders of magnitude, creating flow conditions that bore no resemblance to any historical flood events in the valley. The flow regime transitioned rapidly from initial freefall conditions at the breach to supercritical flow in the downstream channel, with flow velocities exceeding 20 meters per second in confined valley sections. The reservoir emptying process occurred over a period of approximately 12 to 15 minutes according to witness observations and subsequent hydraulic reconstruction. This time frame reflects the interaction between declining reservoir head and the fixed geometry of the breach opening. As the reservoir water level dropped, the available hydraulic head decreased, reducing the discharge rate in a nonlinear fashion that extended the overall emptying duration beyond what would occur with a constant head condition. The physical evidence from the breach zone indicates that the concrete arch elements failed primarily through foundation loss rather than material overstress. Post-event examination revealed that individual arch segments remained largely intact, having rotated and displaced as rigid bodies when their buttress supports collapsed. This failure pattern confirms that the multiple arch structural configuration possessed adequate strength to resist the applied hydraulic loads, but that the foundation interface could not provide the assumed level of structural continuity. The seepage-induced foundation failure mechanism that triggered the collapse involved progressive enlargement of water infiltration paths at the masonry concrete interface. This process began with minor imperfections in the contact surface that developed during construction or early operational phases. Under the sustained hydraulic gradient created by the full reservoir, these initial defects provided pathways for water penetration that gradually enlarged through erosion and piping mechanisms. The foundation undermining process accelerated as the effective contact area between concrete buttresses and masonry foundation decreased. This reduction in bearing area created stress concentrations that exceeded the bearing capacity of the remaining contact zones, initiating a feedback mechanism where foundation loss accelerated further seepage development. The process continued until the remaining foundation contact became insufficient to resist the overturning moment created by reservoir pressure. The critical threshold for structural failure occurred when the effective foundation bearing area decreased below approximately 30% of the original design area, based on analysis of the failure geometry and loading conditions. This threshold represents the point at which the eccentricity of the resultant force exceeded the kern of the remaining foundation contact area, creating tensile stresses that the masonry-concrete interface could not accommodate. The time scale for this foundation degradation process extended over several weeks or months prior to the visible collapse. The gradual nature of the deterioration meant that the structure continued to appear stable even as its actual safety margin decreased towards zero. This extended degradation period created conditions where normal operational activities and routine inspections provided no indication of the developing structural emergency. The failure propagation mechanism that destroyed multiple buttresses in rapid sequence reflects the statically indeterminate nature of the multiple arch structural system. When the initial buttress failed, its load was redistributed to adjacent elements that were already operating near their reduced capacity due to foundation degradation. This load redistribution created a progressive collapse sequence, where each subsequent failure increased the loads on remaining elements, accelerating the overall collapse process. The hydraulic forces generated during the breach discharge process created secondary failure mechanisms that extended the breach opening beyond the initial structural collapse zone. The high-velocity flow through the initial opening generated significant scour forces that undermined adjacent structural elements and enlarged the effective discharge area. This hydraulic enlargement process continued until the breach geometry achieved a quasi-equilibrium configuration determined by the flow capacity requirements and local scour resistance. The flow pattern through the breach created complex three-dimensional flow conditions that maximized energy dissipation within the immediate failure zone while minimizing energy loss that might have reduced downstream flow velocities. The irregular breach geometry generated significant turbulence and flow separation, but these effects primarily influenced local erosion patterns rather than substantially reducing the momentum of the downstream flood wave. The transition from reservoir discharge to valley flow involved complex hydraulic phenomena, including flow regime changes, energy conservation principles, and momentum transfer mechanisms. The initial supercritical flow regime established at the breach maintained its character through most of the downstream valley, with flow depths and velocities determined primarily by valley geometry and roughness characteristics rather than normal hydraulic control features. The flood wave propagation through the downstream valley system followed predictable patterns based on shallow water wave theory, with wave speed and attenuation characteristics determined by local topography and channel roughness. The wave maintained destructive velocities throughout its 21-kilometer travel distance, reaching the valley terminus approximately 45 minutes after initial dam failure. This travel time reflects average wave speeds of approximately 8 meters per second, consistent with theoretical predictions for flood waves in steep mountain valleys. The physical damage patterns observed throughout the affected valley system provide direct evidence of the flow characteristics and energy levels associated with the flood wave. Structural damage to buildings and infrastructure indicates flow velocities and depths that confirm the hydraulic reconstruction of the event. The selective nature of the destruction, where some structures survived while others were completely destroyed, reflects the complex flow patterns created by valley geometry and local hydraulic conditions. The debris transport mechanisms activated during the flood wave passage contributed significantly to the destructive capacity of the flow. Trees, building materials, and sediment entrained by the initial wave increased the bulk density and impact forces of the flowing water. This debris loading created impact forces that exceeded those associated with clear water flow, contributing to structural destruction patterns that would not have occurred with clear water alone. The energy dissipation processes that eventually terminated the destructive phase of the flood occurred primarily through valley expansion and flow spreading as the wave reached broader valley sections. The confined mountain valley geometry that maintained high flow velocities through the initial 20 kilometers of travel eventually gave way to broader valley sections, where flow energy could be dissipated through lateral spreading and increased bottom friction. The thermodynamic analysis of the energy conversion process reveals that the potential energy stored in the elevated reservoir water was converted almost entirely into kinetic energy during the breach discharge phase, with minimal energy loss through turbulence or heat generation. This efficient energy conversion process maximized the momentum available for downstream propagation, creating flow conditions that maintained destructive capacity throughout the extended travel distance. The hydrodynamic instabilities that developed during the reservoir emptying process created complex flow patterns that influenced both the breach enlargement process and the characteristics of the downstream wave. These instabilities, generated by the interaction between declining reservoir levels and fixed breach geometry, created pulsating flow conditions that contributed to the erosive forces affecting the remaining dam structure. The point of no return for the failure sequence occurred when the foundation bearing capacity decreased below the minimum required to resist overturning under normal reservoir loading. This threshold was reached several days or weeks before the visible collapse, but the continued structural stability during this period masked the actual proximity of catastrophic failure. Once this threshold was exceeded, the collapse became inevitable regardless of any operational measures that might have been attempted. The immediate aftermath of the Gleno Dam collapse created conditions that fundamentally altered the downstream valley environment, transforming a controlled alpine watercourse into a zone of ongoing hydraulic instability and secondary hazard development. The passage of the initial flood wave, while representing the most catastrophic phase of the disaster, marked only the beginning of a complex sequence of secondary effects that would continue to threaten downstream communities for hours and days following the primary structural failure. The flood wave propagation through the downstream valley system created temporary hydraulic conditions that bore no resemblance to natural flood events or design flood scenarios considered during the original infrastructure development. As the wave advanced through the narrow valley sections, it encountered numerous constrictions, bridges, buildings, and other obstructions that created complex flow patterns and localized impoundments. These interactions between the flood wave and existing infrastructure generated secondary flooding mechanisms that extended the duration and geographic extent of the disaster beyond the immediate path of the primary wave. At several locations along the flood path, the interaction between the advancing wave and natural or artificial constrictions created temporary impoundments that accumulated significant water volumes before failing catastrophically and releasing additional flood surges. The most significant of these secondary impoundments occurred at the village of Dezo, approximately 5.5 kilometers downstream from the failed dam, where debris accumulation and topographic constriction created a temporary lake that persisted for approximately 6 minutes before failing and releasing an additional surge toward downstream communities. The formation of this temporary impoundment at Dezo resulted from the interaction between the advancing flood wave and a natural gorge section that normally constrained the river flow. The debris load carried by the flood wave, including trees, building materials, and sediment, accumulated at this constriction point and created a temporary dam effect that significantly altered the flow characteristics downstream. The volume of water retained in this temporary impoundment reached approximately 200,000 cubic meters before the debris dam failed and released a secondary flood wave. The failure of the Dezo impoundment created flow conditions that posed immediate threats to the village of Angolo, located approximately 12 kilometers further downstream. The secondary flood wave generated by this failure propagated through the intervening valley section with sufficient energy to cause additional structural damage and prolong the emergency conditions affecting downstream communities. This secondary wave, while smaller than the initial dam break flood, maintained velocities and depths sufficient to threaten life safety and cause significant property damage. Similar secondary impoundment formation occurred at multiple locations throughout the affected valley system, creating a series of temporary retention and release cycles that extended the overall duration of the flooding event. Each of these secondary impoundments altered the timing and magnitude of flow arrivals at downstream locations, creating uncertainty regarding the progression of the disaster and complicating emergency response efforts. The debris accumulation processes activated during the floodwave passage created long-term hazards that persisted well beyond the immediate flooding event. Large quantities of building materials, vegetation, and sediment were deposited throughout the valley system, creating potential dam formation sites that could impound future normal flows or create additional flooding during subsequent precipitation events. These debris accumulations required extensive cleanup operations to restore normal drainage patterns and eliminate ongoing flood hazards. The geomorphological changes induced by the flood wave passage fundamentally altered the hydraulic characteristics of the affected valley system. Channel, scour, and fill patterns created new flow paths and eliminated existing hydraulic controls, changing the flood capacity and flow distribution characteristics throughout the downstream valley. These changes created ongoing uncertainties regarding the flood response characteristics of the modified channel system. The structural damage patterns observed throughout the valley system revealed the complex interaction between flood hydraulics and infrastructure vulnerability. Buildings and infrastructure elements that survived the initial wave passage often suffered progressive failure during subsequent hours as foundation undermining and structural fatigue accumulated. This progressive failure mechanism extended the period of active structural collapse well beyond the immediate flood wave passage. The emergency response capabilities available in the affected valley system were rapidly overwhelmed by the scale and complexity of the disaster. Communication systems failed as telephone lines and transportation infrastructure were destroyed, preventing coordination of rescue efforts and evacuation procedures. The isolation of affected communities created information gaps that persisted for hours and complicated efforts to assess the extent of casualties and property damage. The social response mechanisms activated by the disaster revealed both strengths and limitations in the community's capacity to respond to catastrophic events. Local residents demonstrated remarkable resourcefulness in conducting immediate rescue operations and providing mutual assistance, but the scale of the disaster exceeded local response capabilities and required external assistance that was delayed by communication and transportation failures. The regional emergency response infrastructure available in 1923 reflected the limited disaster response capabilities typical of the period. Professional emergency services were minimal, and disaster response relied primarily on local community resources and improvised coordination mechanisms. The absence of established disaster response protocols and communication systems significantly hampered efforts to provide timely assistance to affected communities. The medical response to the disaster was constrained by both the limited medical infrastructure available in the Alpine Valley system and the destruction of existing medical facilities by the flood wave. The nearest substantial medical facilities were located in valley towns that were themselves affected by the flooding, creating challenges in providing medical care to injured survivors. The transportation infrastructure damage further complicated medical evacuation procedures for seriously injured individuals. The economic disruption caused by the disaster extended far beyond the immediate property damage and casualties. The destruction of industrial facilities, transportation infrastructure, and agricultural areas created long-term economic impacts that affected the entire regional economy. The loss of electrical power generation capability eliminated a significant source of regional economic activity and disrupted industrial operations throughout the broader area. The environmental consequences of the disaster included significant ecological damage to aquatic and terrestrial ecosystems throughout the affected valley system. The flood wave destroyed riparian vegetation, altered stream channel morphology, and deposited sediment and debris that affected water quality and aquatic habitat conditions. These environmental impacts created long-term consequences for local ecosystems that persisted for years following the immediate disaster. The investigation and recovery efforts initiated following the disaster revealed significant limitations in the available forensic and engineering analysis capabilities. The absence of systematic data collection procedures and forensic analysis protocols meant that much of the technical evidence regarding the failure mechanism was lost or inadequately documented. This limitation significantly hampered efforts to understand the precise causes of the failure and develop appropriate prevention measures for future similar structures. The legal and administrative response to the disaster reflected the limited framework available for addressing technological disasters in the early 20th century. The absence of established liability principles and compensation mechanisms for technological failures created prolonged legal proceedings that failed to provide adequate relief for disaster victims, while also failing to establish clear responsibility for the engineering failures that caused the disaster. The long-term community recovery process revealed both the resilience and vulnerability of alpine communities facing catastrophic infrastructure failures. While local communities demonstrated remarkable capacity to rebuild and recover from the physical destruction, the social and psychological impacts of the disaster created lasting changes in community character and risk perception that influenced subsequent development patterns and infrastructure decisions. The technical lessons derived from the disaster were constrained by the limited engineering analysis capabilities available during the period. The absence of systematic failure analysis methodologies and limited understanding of complex structural failure mechanisms meant that many of the critical technical insights regarding hybrid structural design and progressive failure mechanisms were not recognized or incorporated into subsequent engineering practice. The regulatory and policy responses to the disaster reflected both the recognition of the need for improved dam safety oversight and the limited technical and administrative capabilities available for implementing effective safety measures. While the disaster prompted increased attention to dam safety issues, the technical understanding and regulatory framework necessary for addressing complex structural failure mechanisms remained inadequate for preventing similar future failures. The forensic investigation of the Gleno Dam failure, conducted in the aftermath of the December 1923 disaster, represented one of the first comprehensive, technical examinations of a major infrastructure collapse in the early era of reinforced concrete construction. The physical evidence recovered from the failure site, combined with witness testimony and documentary analysis, provided crucial insights into the failure mechanisms that would fundamentally influence dam engineering practice and regulatory oversight for decades to follow. The post-disaster site examination revealed a failure pattern that contradicted many of the initial assumptions regarding the structural adequacy of multiple arch dam designs. The concrete arch elements, rather than exhibiting the material failures anticipated in conventional structural analysis, remained largely intact as individual structural components. The failure had occurred primarily through the loss of foundation support, with individual arch segments having rotated and displaced as rigid bodies when their buttress supports collapsed due to foundation undermining. Physical evidence at the buttress foundation interfaces showed clear signs of progressive water infiltration and erosion that had occurred over an extended period prior to the visible structural collapse. The examination revealed erosion channels and void spaces at the masonry-concrete interface that indicated sustained seepage activity. These erosion patterns demonstrated that water had been penetrating the foundation interface for weeks or months, gradually reducing the effective bearing area until structural failure became inevitable. The Technical Examination Commission, led by engineers Ganasini and Danuso, documented the precise geometry of the failure zone and analyzed the structural loads and material properties involved in the collapse sequence. Their investigation confirmed that the concrete materials and construction quality met the specifications established for the project, ruling out material deficiencies as the primary cause of failure. The investigation focused instead on the adequacy of the foundation design and the performance of the masonry-concrete interface under operational loading conditions. The forensic analysis revealed that the original design calculations had been based on the assumption of full contact between the concrete buttresses and the masonry foundation, with load transfer occurring uniformly across the entire bearing surface. However, the physical evidence demonstrated that effective contact had been lost over significant portions of the bearing area due to construction imperfections and subsequent seepage-induced erosion. This reduction in effective bearing area had concentrated loads on smaller contact zones, creating stress levels that exceeded the bearing capacity of the remaining foundation interface. The investigation documented several critical design assumptions that proved invalid under actual operating conditions. The assumption that visual inspection could adequately monitor the structural condition of the foundation interface was contradicted by evidence showing that extensive undermining had occurred without producing observable surface indications. The assumption that the masonry and concrete materials would behave as a monolithic structural unit was contradicted by evidence of differential movement and progressive separation at the material interface. The forensic examination also revealed that the multiple arch structural configuration, while structurally adequate for the applied loads, created a failure mode that differed significantly from conventional gravity dam failures. The statically indeterminate nature of the structural system meant that the loss of support at any single buttress location would redistribute loads to adjacent elements, potentially triggering progressive collapse if multiple buttresses were simultaneously compromised by foundation degradation. The technical investigation established that the seepage-induced foundation failure mechanism represented a previously unrecognized vulnerability in hybrid masonry concrete dam designs. The gradual nature of the foundation degradation process, combined with the absence of effective monitoring techniques for detecting subsurface erosion, created conditions where catastrophic failure could occur without advance warning through conventional inspection procedures. The regulatory investigation revealed significant limitations in the approval and oversight procedures that had governed the dam's design and construction. The review process had focused primarily on static structural analysis calculations without adequately addressing the unique failure modes associated with the experimental hybrid design configuration. The investigation documented the absence of specific design criteria or construction specifications for the critical masonry concrete interface that ultimately determined the facility's structural adequacy. The legal proceedings that followed the disaster, extending from 1924 through 1928, examined questions of professional responsibility and technical competence in the design and construction process. The proceedings ultimately resulted in acquittals for all defendants, reflecting the conclusion that the failure resulted from inadequate technical understanding of hybrid structural behavior rather than professional negligence or deliberate misconduct. This outcome highlighted the experimental nature of the design approach and the limitations of contemporary engineering knowledge regarding complex structural interactions. The broader technical community response to the disaster included extensive analysis and discussion in professional publications throughout Europe and North America. The failure was recognized as providing crucial insights into the behavior of reinforced concrete structures and the importance of foundation design in hydraulic structures. The case became a standard reference in structural engineering education and was incorporated into dam design guidelines and regulatory frameworks throughout the international engineering community. The specific technical lessons derived from the Gleno failure influenced numerous aspects of subsequent dam engineering practice. Design procedures were modified to require more detailed analysis of foundation interface behavior and to specify construction techniques that would ensure adequate bond development between dissimilar structural materials. Inspection and monitoring procedures were enhanced to include methods for detecting subsurface deterioration and progressive foundation failure mechanisms. The disaster prompted significant changes in regulatory oversight procedures for dam construction and operation. New requirements were established for independent technical review of experimental design configurations, and enhanced inspection procedures were mandated for facilities incorporating innovative structural approaches. The regulatory framework was expanded to address ongoing monitoring and maintenance requirements throughout the operational life of major hydraulic structures. The environmental and social impact assessment procedures developed following the disaster represented early recognition of the broader consequences associated with infrastructure failures. The investigation documented not only the immediate casualties and property damage but also the long-term environmental and economic impacts affecting the entire regional community. This comprehensive impact assessment approach influenced subsequent disaster response and infrastructure planning procedures. The technical documentation procedures established during the forensic investigation created precedents for systematic evidence collection and analysis that would influence future infrastructure failure investigations. The detailed documentation of physical evidence, witness testimony, and technical analysis provided a comprehensive record that continued to inform engineering practice and regulatory policy for decades following the disaster. The international technical exchange generated by the disaster investigation contributed to the development of improved design standards and construction procedures for hydraulic structures worldwide. The technical insights derived from the failure analysis were incorporated into design codes and professional practice guidelines throughout Europe and North America, influencing dam engineering practice well into the modern era. The long-term monitoring and research programs established at other similar facilities following the disaster provided valuable data regarding the performance of multiple arch dam designs under various operating conditions. These monitoring programs contributed to improved understanding of structural behavior and helped identify potential problems at other facilities before they reached critical stages. The educational impact of the disaster extended beyond immediate technical lessons to influence broader approaches to engineering education and professional practice. The failure became a standard case study in engineering curricula, illustrating the importance of understanding complex structural interactions and the limitations of conventional analysis procedures when applied to innovative design configurations. The disaster's influence on professional engineering practices included enhanced requirements for peer review of experimental designs and improved documentation procedures for construction quality control. Professional engineering organizations developed new standards for technical competence and professional responsibility that reflected lessons learned from the investigation of complex infrastructure failures. The economic analysis of the disaster's impacts revealed the broader societal costs associated with infrastructure failures, including not only immediate casualties and property damage, but also long-term economic disruption and environmental degradation. This comprehensive cost assessment approach influenced subsequent infrastructure investment decisions and risk assessment procedures. The Gleno disaster ultimately demonstrated that technological progress in engineering design must be accompanied by corresponding advances in monitoring, inspection, and maintenance procedures. The failure illustrated the dangers of applying conventional oversight procedures to innovative structural configurations that may exhibit failure modes not anticipated in traditional engineering practice. The systematic documentation and analysis of the failure mechanism provided a foundation for understanding progressive deterioration processes in complex structural systems. The technical insights derived from the investigation contributed to the development of modern structural health monitoring techniques and failure analysis methodologies that continue to influence infrastructure engineering practice today. The disaster's legacy in dam engineering practice includes not only specific technical improvements, but also a broader recognition of the importance of conservative design approaches when dealing with experimental structural configurations. The failure demonstrated the critical importance of maintaining adequate safety margins and monitoring capabilities when implementing innovative engineering solutions in critical infrastructure applications.